Hi, I'm Eric Johnson. I'm a technical program manager working in Seattle's Google office on the compute engine team. So today what I wanted to do is just spend a couple minutes to give you a kind of a whirlwind tour of Google Cloud Platform. How many, just show of hands, how many people were at the keynote and saw Brendan Burns talk? Everybody, okay, so you're going to recognize a few slides, but I'll go into a little bit more detail than he did on a couple of these things. And then we'll do a deeper dive on compute engine specifically, and then we'll do a little demo that shows you how you can use Salt to spin up compute engine instances. So first, kind of like, why would you choose Google Cloud Platform? So like Brendan said, same kind of slide here. So over the past 15 years, we've been iterating on this quite a bit. Google, I think, was one of the first ones to start innovating a lot in the data center space and building out custom hardware, networking, and server hardware in terms of being able to scale up with demand of users across our application suite. We also have a global network. So one of the things that we try and do at Google, if you use a Google service, we try and make sure that we have a presence close to large population of users, and we try and get you onto our network as quickly as possible. Our network's pretty blazing fast, so it benefits a lot in terms of usability and performance, low latency, responsiveness of the applications to get you on our network faster. So we do a lot in terms of edge caching, content, and stuff like that. So a lot of speed improvements there on the network. We also do a lot of innovations sort of on the software side of things. So as we have continued to build out additional services, or acquisitions like YouTube, our user base continues to grow phenomenally. And in order to be able to support a lot of that stuff, we spent a lot of time developing distributed scalable systems. As we would go through and we would develop these systems and use them internally, we would end up discovering that we would reach bottlenecks or issues that in terms of scalability of those applications as well, or those distributed systems. And so we would continue to iterate on that stuff too. A lot of these Google has published white papers on, so I think GFS and MapReduce, those white papers have been out for years and years. A lot of this stuff has been the foundation of a lot of open source projects out there, like Hadoop or Cassandra have been built on a lot of the conceptual knowledge that was released in these white papers. These are systems that we use internally, but have long since retired because they didn't scale up to what we needed them to. So we're kind of moving beyond that. So what does that mean? Like, so when you kind of merge all of that stuff together, right? Like we've got great data center efficiency, hardware, networks, global network that's fast around the world, innovating on these distributed scalable systems. Those are the things that really are what allow Google to power applications that serve millions of users a day or hundreds of millions of users a day. So a lot of the big ones, right, like Google Maps and Gmail, YouTube, these things are just serve massive amounts of users. This is a quote from Stephen Levy in Wired magazine. I think this is a great quote. Google's ability to build, organize, and operate a huge network of servers and fiber optic cables with an efficiency and speed that rocks physics on its heels. This is what makes Google Google. It's physical networks, thousands of fiber miles, and those many thousands of servers that in aggregate add up to the mother of all clouds. So this is data centers, like I've been on one data center tour at Google. Actually, I've been on several data center tours at various companies, and these things are just phenomenal. Wish I could go there a lot more. So Google Cloud Platform, right? So that was why you would be interested in using Google, right? So you get a lot of scale at your fingertips. But so these services that I'm going to kind of step through pretty quickly are all built on these technologies behind the scenes. They're all using the Google network. They're all using Google servers. All of these innovations that we've made through software and hardware and data center and network are what's used to build these cloud services that we've now basically externalized and made available to you. So kind of drilling down in a couple of these, we've got sort of our compute services. We have App Engine that's been around quite a while. That's our platform as a service. So high level, really, if you're building a web application and you're not kind of like porting something over, maybe legacy, but you're looking at building out a web application and you want to not have to worry about scaling up or down. You just want to be able to service demand when it shows up. You've got content out there that gets virally popular, and you don't need to worry about like answering a pager and going and provisioning additional capacity for that. It just handles it on the fly. So that's what you'd want to look at App Engine for. And we have runtimes available in Go, Python, Java, and PHP. Compute Engine, I'm just going to kind of skip over that because I'll do a deep dive on that. Storage options, we have cloud storage. So this is it's blob storage. And I think this is out of cloud services, both cloud storage like this or blob storage. And virtual machines are the things that have been around in cloud the longest, right? So everybody's probably familiar with cloud storage. I think a couple things that, for me, stand out with cloud storage that I feel are really attractive for this service is everything sort of gets edge cached out. Like our objects can get edge cached out. So this is taking advantage of Google's network. It's not a CDN per se, right? We don't have a separate CDN service that you need to like kind of plug into or access to be able to get your content out there. It just uses Google's network for that. GCS, or cloud storage here, also has a read after write consistency. So some of the other ones you might be used to are eventually consistent, right? So strong read after write consistency, what that means is if you, for instance, you make a change to the system, like you delete an object and you were to immediately follow that up with a GET request, it's going to 404. I mean, when we tell you it's deleted, it's gone. It supports versioning. So there's a lot of great tricks to cloud storage. Cloud SQL, it's our fully managed MySQL in the cloud. So if you have an application that's already using MySQL, we've just recently come out with the ability to support native MySQL wire protocols over port 3306. So if you have an application and you don't want to have to deal with managing your MySQL server anymore, you can just basically change a couple configuration parameters and drop in this as a replacement, and we do all the replication and backups for you. Cloud Data Store is our schemaless, like NoSQL type data store, designed to really scale up to like trillions of transactions. Although it's like a NoSQL type data store, it does have a SQL-like syntax. So there is kind of a lower learning curve over other traditional, say, NoSQL type systems where you might have to kind of take a step back and rethink how your brain works. It's still non-relational, but it gives you that kind of like SQL interface, so it's sort of a low learning curve on that. On our sort of app services, we have BigQuery, and even though I'm on the compute engine team, BigQuery to me is amazing. So this system is designed for basically processing ad hoc queries against multi-terabyte data sets. They just recently came out with a feature that allows real-time streaming into the service. And so you can basically query over your data set as it's going into BigQuery. I've seen, we have a YouTube channel called Google Developers Live. And they've got an interview with one of our DevRel people that have another company that's built some applications on top of BigQuery. And it's just phenomenal how they've instrumented not only just how their service works, but also how their application is performing. So they're tracking things like profiling their application and using BigQuery to get real-time updates on how that's impacted. If they roll out a new release, they identify a regression right away. It's amazing stuff. Cloud endpoints, if you have your own custom code and you want to build a REST interface on that, Cloud endpoints allows you to basically host that REST API. It also has support for basically auto-generating client libraries. Back-end support for like iOS and Android. So if you're a mobile developer, this is a great service for you to be able to develop like a REST endpoint, generate client libraries for that. All right, so Google Compute Engine next. So Compute Engine is our infrastructure as a service offering, and it basically consists of virtual machines, network, and storage. And Google DNA throughout, right? So this is going back to a few slides what I was talking about, right? So it's built on top of the technologies that Google has in-house to give you the speed, scale, reliability, and security that you've come to expect from all Google applications. And now it's available here to power Google Compute Engine. Fast provisioning, consistent performance. So I have a little demo. I'll show you how quickly we can provision instances. Compute Engine went generally available in December last year. And with that, we really feel like this is it's enterprise ready, it's solid. We've got SLAs in place. Support is available to you, lots of certifications. And for accessibility, we have a web interface, which is really handy. And I'll kind of show you that a little bit too. We bundle up command line utilities that access all of our cloud services. And the one that allows you to access Compute Engine is called GCUtil. It's a Python script that just uses our public APIs. We also just exposed a REST API if you wanted to write your own stuff, and that's where I did the Salt Cloud integration. So I'll show you that down the road also. And a lot of partners, and I think I have a slide that lists a few of those. So with that, let's show you how these things spin up. I think I'll just switch over. So this is a little demo that we have here. And what I'm going to do is kick off a request to spin up 1,000 persistent disks. And I'll tell you a little bit about persistent disks as this is going on. But to kind of give you a little overview of what this demo does, is it's drawn out 1,000 boxes here. Each of those boxes represents one of the persistent disks that's being provisioned. And as this timer runs along, I may need to restart this. I should have tested that a little sooner. So as it's going along, it's basically sending out requests to create the persistent disks. And the squares should be changing color here, which is unfortunate that that hasn't started yet. And as they flip over to a green status, then the persistent disk is completely ready. Also, what's happening behind the scene here on this demo is when the persistent disk is created, the operating system image is being loaded onto the disk itself. So that I'll flip over to another one and show you how to spin up the virtual machines that are then going to use these as their root device. So let me just apologize for this. I think I'm going to have to flip over. Ah.
The Wi-Fi strikes again.
I did this right before. Did I maybe pick the wrong room?
No, I think it just reset.
Yeah.
I'll have some feedback for you later. All right. Let's just see what happens here. There we go. OK. Wi-Fi. All right, so the green ones, they're provisioned. They have the operating system loaded on it, and the disk is ready. So if there was an instance, we could just attach it right away. So while that's cooking in the background, let me go back over to the demo, and we'll talk a little bit about persistent disk. So you can use persistent disks both as a boot partition as well as just a separate data disk, and you can attach multiple disks to an instance. You're billed only on capacity, not on IOPS plus capacity or anything like that. So whatever your storage is, that's what you pay for. Performance caps scale linearly with size. So if you do start to run into some IOPS issues or bottlenecks, you can add additional disks or go back and create a larger disk, and you get more IOPS out of that. Differential snapshots, I'll talk a little bit about that in a second. From those snapshots, you can create additional persistent disks as well. So it's a great way for you to go ahead and start out maybe with a base operating system image, go in and customize it the way you want, create a snapshot, and then use that to create additional persistent disks that in turn you can use for new VMs that you spin up. 10 terabytes here, I've got a nice, great big number there. So you can have an instance with a single persistent disk of up to 10 terabytes, or you could have multiple disks for a total of 10 terabytes on a particular VM. Depending on the size of the VM, you can kind of have more or less disks. Use cases on this. So over on your left, I guess, we talked about this, right? So you're using it as a root device. The little box on top represents a VM. The middle use case there is you're using sort of two persistent disks. One is just a separate data disk. And then the third use case over there is that you can take a persistent disk and mount it across multiple VMs in read-only mode. So you can only have it mounted to one instance in read-write, but if you wanted to use that basically to load up a bunch of data that you then wanted to share out across the multiple images in a read-only fashion, you unmount it, and then you can mount it against read-only against multiple instances. So the global snapshot and restore. So this is also a great way for moving your data around. So you see over here in the top box, this is our US Central 1 zone. And I've got an instance with some disks there. And when I create a snapshot, that snapshot is stored in Google Cloud Storage. And because Google Cloud Storage replicates globally, I can go drop down into our Europe zone, and I can create a persistent disk that's based off of that snapshot. So I've effectively mirrored my data from one region of the world to another region. Then I can spin up an instance using that persistent disk. So it's a great way to sort of replicate your data and move it around if you decide that you need to service something in a completely different region. So let's pop back and see how our disks are doing. All right, done. So 1 minute and 44 seconds to do all 1,000. So while we do virtual machines, let's go ahead and let me flip this over. So now we're going to create 1,000 virtual machines, and each one of those virtual machines is going, it's given a name, and that name is going to also go out and try and find a persistent disk that has that same matching name and use that as its boot device. So again, you see the colors kind of flipping through here as the instances are going from sort of the request was received to, okay, I'm provisioning your instance, to getting into the completed state, and when it goes to green, it's basically ready. SSH usually takes another second or whatever, but basically the operating system is up and alive at the point where it's green in this particular demo. So while that's cooking, let's go back here. So machine types. So this is the different sizes of machines that you can get. And so based on your workloads, you might want to take a look at what options are available to you. So it's basically a CPU memory ratio. Our standard one is kind of an equal sort of mix, and you can go all the way up to 16 cores and 60 gigs of RAM. There's the high mem distributions there, that middle band. So again, 16 cores, 104 gigs of RAM if you need it. And then we also have high CPU, low memory requirement. So 16 cores with just 14 gigs of RAM. And then down in the lower left, I've got shared core instances. So if you wanted to just do some like quick and dirty prototyping or small little things that you don't really care too much about in terms, not really performant, we can go down. I think they go down to about like half a gig of RAM, and it's a shared core, single core. So those are available to you as well. For images, we basically support pretty much most Linux/BSD type images right now, not Windows yet. And we have custom kernels now, so you can basically roll your own. There's procedures on our documentation on how you could actually go out if you wanted to get, say, Arch Linux or something like that up and running. Does anybody ever use Arch Linux? Just one guy in the back? Yeah, no, there's a couple, sorry. It was a joke with Joseph. I know he's a big Arch fan. So let's see, sub-hour billing. Let's say you have a job that you're only going to need a Hadoop cluster you're going to spin up, and you're going to process something for 15 minutes. You're only going to get charged for 15 minutes, right? So 10-minute minimum. But after that, it's just basically by the minute. So you don't, as soon as you're done, you tear them down and you're done paying for that stuff. Enhanced reliability. So when we were in beta, this was feedback we got from a lot of folks. When we would have data center maintenances, we would sort of force users to have to kind of move their instances around based on our maintenance schedule. So we've come out with some new features now, live migration and automatic restart. So if there is some sort of an issue within our data center, whether it's a planned maintenance or maybe a machine itself just croaks over and dies, we've got some mechanisms now in place to keep your virtual machines up and running. So live migration is pretty good in terms of it'll keep the instance up and running and live and responsive while it's being migrated live. So you may see some performance degradation, but it's not going to be a full-on, like, all connections dropped, completely unavailable while it gets rebooted someplace else. Automatic restart, that's just if like there's a particular hardware failure on our side, it'll just automatically come right back up again. So let's see, I think I probably talked long enough. Sorry, I'm not too good with the tab thing. All right, so 3 minutes for 1,000 virtual machines, plus, what was it, 1:44 for the disks. So we're doing 1,000 instances in less than 5 minutes. These are all fully provisioned, SSHable. They have their operating system up and ready for you. So this kind of speaks a lot to the DNA factor, right, of Google, right? We're using the same software and technology that powers a lot of our applications, like YouTube and Gmail and stuff, to provide the service to you. They kind of have to, you want to make sure like the disk exists first. So you could probably do some timing there to make sure that you've got like the first couple of hundred. But that particular demo does a lot of batching requests, so it'll just send a great big batch. And so they're not necessarily guaranteed to be processed in a specific order. So I'd say you're better off probably pre-provisioning the disks.
It's only a minute.
Yeah, for 1,000, right? So yes?
What size were the disk in the
10 gigs.
10 gigs?
Yeah.
That's for the disk or both? Both are 10 gigs.
The image that we use, we create basically a 10 gig root partition or boot disk, and we load the entire OS up on that, and that's what we provisioned there for 1,000 of those. I think the demo uses the CentOS image. Okay. It could be Debian. I might be mistaken on that. But I think by default, if you're going to just spin up a regular disk with one of our default images, it's the ext4. But you can, if you create basically an empty persistent disk, it's not formatted at all. So you can go in and format it and put whatever file system you want as long as the image and the kernel would support it.
And they're all hard drives or flash drives?
I don't know what it is. Sorry. I don't know.
So it's networked?
Well, it's networked, right? But like behind the scenes, I don't know like if it's an actual hard drive or maybe it's a big SAN. Probably not, but.
It's a network sharded drive, but we do not offer infrastructure. It's a network, so it's not SSD.
So on the networking side, so it's Google's network, right? I talked a little bit about how large that network is and how close we make points of presence to users and how we cache things as close to users as possible. So the same thing holds true here for Compute Engine. We're using Google's network, so you get speed and scale. Within Google Cloud, you have projects. And each project within Compute Engine, as you spin up instances within that project, they belong to a private network. So they'll get a private IP and 10 dot space. That's private completely to that particular project. So even if you, as an account holder, were to create multiple projects, those projects are isolated from each other, even though you own them all and you're paying for them all, but they're isolated. TCP, UDP, ICMP. We support tagging of networks and address ranges and instances. And so that's an easier way, as we talked about firewall rules, for you to be able to create rules based on tags versus having to think about IP ranges. For IP addresses, for public IP addresses, we have both static and ephemeral. By default, they're ephemeral, but you can actually request static IP addresses and keep them for whatever. Yeah, and you pay for it. Private IPs, like I said, they're ephemeral, but there's the concept of internal DNS name resolution, or DNS. So when you create instances, you give them a name, and all the projects within that, all the machines within that project can refer to each other's instance just by name, and that gets resolved automatically. So even if you had an instance, let's say, and you shut it down for a couple of days and you brought it back up and it got a different private ephemeral IP, you can still refer to it by its host name. Advanced routing supports gateways and VPNs, IP forwarding. On our load balancer, This is a relatively new feature. I think we came out over the summer. It's region-based, and within regions we have multiple zones. So you'll see here the big gray box is our US Central 1 region, and within that I've got yellow boxes over here on the right-hand side of US Central 1A as one zone and 1B as another zone. A firewall or a load balancer consists of three sort of resource objects. There's a target pool, which is your collection of instances. And then you have a forwarding rule, which basically says, for what protocols and ports do you want to forward to what sets of, or what target pool. There's also an optional HTTP health check. So if you wanted to see whether or not your services were up and running, you can create a separate health check, and it'll just do HTTP checks on that. And if it gets 200, it assumes the instance is OK.
Is there a limit to the size of the target pool?
I don't know off the top of my head if there is such a limit, but it would be very large, I'm sure. There's a link down here. So we did a test and posted this to our blog. This was, we took our load balancer and we scaled it up to 1 million requests per second. And there's details in there. Let's see if I jotted some of these down. So we did 1 million requests per second. And so from the start to the end of the test, we started with an empty project. We spun up instances. We created the load balancer. We set the instances behind the load balancer. So what it consisted of as far as a target pool, there were 200 machines running Apache. They were just our N1 standard ones, so single core machines. 200 of those. To generate the load on that, we had 64 other VMs that were 4-core VMs, throwing like 1,000 concurrent connections at this load balancer. The load balancer, it was just one load balancer object. So there was a single IP that was receiving all of this traffic and distributing it around to the backends. There was no pre-warming of the load balancer. It was just as fast as these 64 load-generating VMs could ramp up and start throwing traffic at it. We ramped up that quickly to serve 1 million requests per second. I think we left it running for like 7 minutes. Total cost $10. So yeah, pretty impressive technology, I think. I encourage you to read more about it if you're interested in the details there. And lastly, kind of noteworthy items, metadata. So we have a metadata service that's available. So if you're inside of a VM, you can access metadata. And this is great for startup scripts, right? Custom startup scripts. And this is also how we handle SSH keys. So if I'm sitting here from my workstation and I want to be able to create a VM and I want to SSH into it, I can generate my keys here, and my public key will get pushed up to the Compute Engine metadata service. And then when the instance boots up, that public key will go down as an authorized host entry, or authorized keys. I forget what the name of the file is. And so then that way I can basically SSH into that machine. Tags I mentioned before. We use OAuth 2 and scopes for accessing other cloud services. So you can, from a Compute Engine instance, you can access cloud storage or data store. And we have a large and growing ecosystem of partners and open source technologies that you can use to fiddle around with Compute Engine. All right, so we're here for Salt, though, so let's talk about Salt. So for this demo, what I'm going to do is show you a little bit about the developers console, and this is our web interface for accessing our virtual machines. And I'm kind of horrible at doing the pretty pictures, so you can tell like the first slides were done by like the marketing people, and the last slides are done by me. So that little green thing is actually what we're going to create, and that's the Salt master, and it's just going to be named Salt. That way, when the minions come up by default, they're going to look for Salt master named Salt, right? So that should just work. And then I've got this little reminder to myself here about a metadata tag. So let's see. What I want to do is I want to create a new instance, and there's some of these fields that are required. So I'm going to name this Salt, and my metadata tag was Salt demo, yep. And we're going to, let's see, choose an image. I'm going to use Debian. So this is, you can select what zone you want. You can select what machine size you want. If you want to boot from a different persistent disk, or this one is going to create a new persistent disk loaded with Debian 7, and then the instance will come up. So I'm just going to go ahead and hit create. That should flip me back over here to my list, and we should see it show up under here. So what's happening if I were to flip over to the disks tag over here, I'd see that the disk was already created now there. So Salt is already up. SSH is probably coming up in the background right now. So this little section here is Compute Engine. Here's my other services available to me. This is all on the developer's console. So I could drill down into these. Cloud storage even has its own web-based navigation system that you can upload and download files to. But for Compute Engine specifically, snapshots, images, you can create, like I said, your own custom images. But let's go back here. So that was that slide. All right, so now what I want to do is use Salt Cloud to create 4 instances and install Apache. And I'm going to kind of walk through this while that Salt master is provisioning. I'm running a custom script, so I'll show you that as it's going. And then we'll come back and I'll do these actual commands. So what we're going to do with this is I'm going to set up that load balancer example that I had earlier. So we'll create 4 minions, and I have a map file that has those 4 minions in it. And I'm going to create a firewall rule. Like I said before, on your project, you have a private network. And by default, we only allow port 22, TCP 22 in. So we have to set a special firewall rule that says go ahead and let TCP 80 traffic come in. And so we're going to create a firewall rule, and then we're going to create the load balancer object. And that will specify both the forwarding rule that says TCP port 80 as well as these 4 minions in the target pool. And then we'll generate some HTTP requests just to prove that it actually works. So this is how I was using metadata and the startup script. So what's happening behind the scenes right now is when the Salt instance, my Salt virtual machine spins up, it line 3 here, it sends a curl. Well, the virtual machine actually queries the metadata service and says, is there a metadata tag called startup script? Yes, OK, great. Its value is this script. And so it pulls this script down and executes it. And so as the script is executing, line 3 makes another call up to the metadata service, and it says, hey, do you have a metadata tag called salt demo? Go ahead and record that value, and then line 5 checks to see if the value is yep. And if so, then it starts executing. And so since this is a Debian 7 image, I'm going to go ahead and install some stuff I like, and I'm going to use pip to install libcloud. And I'm pulling libcloud in at a specific hash because I've got a bug where we fixed being able to post load balancer create. You can attach and detach additional instances, so you could scale up your load balancer or scale it down. So this hash has that fix in it. Line 11, I'm going to boot up the, pull down the bootstrap script and install Salt Master using RC3. And then I've been doing some work on the GCE cloud provider to add additional functionality into it. So I'm going to pull down the copy that I've been working on and just kind of tuck that in on top of what's deployed automatically by Salt. And then I'm going to set up my root SSH keys. So this allows me, if I pull down these keys, I've got, you see on line 20 here, I don't know if I can highlight that with my mouse, but I'm using a utility called gsutil. And that's our command line utility to access cloud storage. So what I'm doing here is I'm saying, I'm going to use gsutil, I'm going to copy a file out of that, and I'm going to pull that down, and that happens to be my root's public key and private key. Set permissions on that. And then I'm also, in lines 24, 25, going to use gsutil to copy down my Salt configuration files that I've set up ahead of time. So it has my Salt cloud provider configuration and my map, and it's got my state files set up. And so I'll show you those. So this is, if you've ever used Salt Cloud before, this should look pretty familiar to you. You've got Etsy Salt Cloud profiles, and I've got 2 blocks there represented by Zone 1A and Zone 1B. And the only difference really between those two is the zone that I'm spinning up the instances, or that I would spin up the instances in. The top block is etc Salt Cloud. Those are my credentials for accessing Compute Engine. And then I have a map file that just says, I'll put the odd number ones in zone 1A and the even number minions in 1B. Pretty straightforward. All right, so let me go over and try and type some commands here. Can everybody see that okay? I hope so. All right, so I'm going to go over here as root.
Scroll up the bottom there, we can't see them.
Do a clear or something.
All right. Okay. So let's see, Salt demo. Okay, so what this is doing is it's using Salt Cloud in parallel mode, using that map file that I talked about to go ahead and provision 4 instances on Compute Engine. And I'm trying to remember if it's done at this point, provisioning those. I don't think it's done. Okay, some of them are done. So now what it's doing is it's taking the local bootstrap shell script and it's pushing that out to the instances. So those 4 instances are pretty much already up and running, SSHable. We're pushing the script across there and we're executing it locally. Because this is the Salt master, it's also generating the Minion keys and it's going to push those Minion keys over as well. And so this will probably just take another couple seconds because if you're not familiar with it, well, I mean, it's the same bootstrap script that you use for everything, right? So it's updating some packages on each of the machines and setting the Debian repository for Salt to pull down the Salt Minion package as well as Salt Common, I think. So that'll take a couple seconds. So I guess this is a good time too. I do have an issue with the demo. Okay, so there they're coming up. So I have a little bit of a problem that I could not get figured out last night. So I apologize. This is some kind of a bug I have with the system. But if I, just to kind of show you. So they're all named Minion, right? So Minion test.ping. Yeah, it's kind of weird. Salt Minion status. So that's kind of weird too. So since I couldn't quite get that figured out, my kind of horrible solution was to just go ahead and SSH over to each of the minions and then just bounce the Salt Minion process. So I'm using our gcutil command line in a shell wrapper, and it's SSHing, sending a command over to do etc init the stop of the Salt Minion, do a pkill in case there was something else hanging around on that, and then start it back up again. So hopefully, if I do this, 1, 2, 3, 4. All right, so that looks a lot better. So I apologize for that. I was, I don't know. I had a hard time trying to figure that one out. And I kind of went off in multiple directions and just didn't get it figured out. All right, so what we want to do now is I want to go ahead and deploy Apache. So what I have, let's see, this is Debian, so I'm pushing out Apache 2. I'm loading a headers module, mod headers, and I'm putting out a custom index.html and some CSS. And I also, so I'll show you we need to do this. So I was talking to Joseph about this. I had built all this functionality into Salt Cloud, but for like creating firewall rules and load balancers. But it sounds like a better place to put this would be inside Salt Util. So I may end up moving that stuff back someplace else. What I'm doing here is I'm just using, these are commands that I implemented in Salt Cloud, and it's using libcloud underneath. And I'm just passing in some of the required parameters, and then this just makes a call over to our public APIs, passing along those required parameters. So for a load balancer, you have to specify the zone that you want it to come up in. You have to give it a name. You have to say what ports it should service, and then you have to tell it, who it belongs to. So I'm using a load balancer as an abstract to kind of wrap both that forwarding rule resource as well as the target pool resource. So it's basically wrapping two API calls, right? One is to create the target pool that gives those 4 members, and then the other one is to create the forwarding rule. And so once this comes back, it should give us the load balancer IP. Which conveniently shows up down here towards the bottom. So if I drop this in here, okay, so there's a Minion 3. But I want to kind of make sure that the traffic is bouncing, right? All right. 2, okay. All right, Google colors too. So this is kind of like a little hack, right, with JavaScript. I didn't want to hit there and mash the refresh button every time. So I'm passing in a query parameter, and then JavaScript pulls that up, and then it uses like set timeout and location href or something like that to send another request. And then I told Apache to shut off all cache control so that everything is a brand new HTTP request. And that concludes my demo. I guess both of my demos. So I'll close it out with what's available now. You can create instances, destroy instances, list sizes, images, locations. You can do a show instance. Those are sort of the default common things across all of the cloud providers. And then I've started working on rounding out more of our feature compatibility for Compute Engine. So things like persistent disks and snapshots. I've got a list of all the functions here that I have implemented. Networks, firewall rules, and then the load balancer. And then there's, like I said, you can also attach and detach additional instances to a load balancer using a specific version of libcloud. But like I said, all of this I have in Salt Cloud, which doesn't sound like a good place to live. But I'm open to anybody's opinions on like where this stuff could go, and I also look for help, right? So we could make this better for everybody. And that's all I have for you. Questions? Thanks. Thank you.
The profile, the Salt Cloud profile, you had a make master. I'm trying to understand how that makes sense for a Google instance in general.
So the question was, I have a GCE instance that I'm using as the master.
No, in the map that you used.
Oh, in the map?
Yeah, in the profile which describes each instance of Google
Oh,
for the Salt Cloud.
yeah. Let me go back to that.
You have make master, so what does that mean?
That just, so it's a directive for the minion that says who its master is. And in this case, it's Salt. So Salt was the name that I gave the virtual machine that was acting as the master, as the Salt master. So this just tells any minions that come up using that particular profile, your master is a guy named Salt.
Okay, make master falls into not a master.
Yeah, so, right. And then line 7, make master means I don't want this guy to be a master. I mean, I think that that's probably the default, but I sort of err on the side of verbosity there. I also have this little thing, line 9, called delete boot PD set to true. So I'm kind of using a trick on this also. When you use Salt Cloud to create a compute engine instance, I kind of tuck in a secret metadata tag that tells you what profile it was used to create it. So when you issue a command to delete it, that instance can check that metadata tag and says, oh, you know what, I belong to this profile. And then the Salt Cloud can then go ahead and take a look at that profile and say, is delete boot PD set to true or false? And if it's set to true, then it also issues a command to delete the boot PD. So little trick with metadata there that Joseph kind of helped me out with. Yes, sir.
I assume there's some magic going on because you named the server Salt, the DNS Salt just resolves.
There is no magic other than Google magic. So that was one of the things that I mentioned. When you're inside of a project, all of the machines that you spin up, you always have to give them a name. That name has to be DNS compatible, and then each instance can find another instance by its name using our internal DNS.
I assume there are some reserved names. I guess how you call HTTP metadata.
I don't think there's a reserved name, like for the actual instance itself, you mean?
Assuming you made a server called metadata.
Oh, I see what you're saying. Yeah. Well, so there's also, you could specify the FQDN. So the metadata service, I think, is called like metadata.internal.goog or something like that. And then a machine itself, a virtual machine that you spin up, has an FQDN that's much longer. But the short names resolve fine. Yes, sir.
So let's say if you're making, like in the future, some kind of complicated setup where you're going to make sure that you modify load balancer rules only after instance actually was spin up and checked. So is there any kind of feedback you get available, like a queue, or there's a listen to the message and see if the resource was actually spun up and
Yeah, so the way that it actually works is when you say, go create an instance, it returns back an operation ID, like a transaction ID. And that transaction ID has like, what time was it created, the current status, which would be like pending or something. And then what you can do is you can poll that, right? And when that operation flips to a done status, you know that the machine has reached that bootable state. It's up and running. It may take another second, like I said, for SSH to fire up, but plus or minus a couple of seconds, you'd be able to SSH in and start using it.
Follow-up question. So what is the status of this project? Is it like a main project, or is it, people are trying to test this out, just have this functionality for Salt and see how it goes?
No, it's for Compute Engine itself, definitely 100% main project, right? Like Google's really invested now in getting into cloud. And I think that you can kind of see that sort of evolution as we started to, like if you just look back over, say, the last year or 2 years, even just Compute Engine itself, right? When we first launched and we were beta and we were sign up only, and then we were open signups, and now we're GA. So yeah, we're definitely 100% driving this stuff forward. We're iterating on it quickly. New features are coming out all the time. Okay, great. Thanks, everybody.